Is this what you think of when you hear someone say the word scientist? Lab coats, test tubes, and some weird experiment gone wild? These are the things Hollywood would have us believe. For many people, this is the image they have of a scientist. Of course, it is far from the truth. Actually, most scientists today work in teams because everyone knows teamwork often accomplishes more than individuals working alone. When people work together on a project, there is a better chance for the brainstorming of ideas and creative thought. Often one person's idea will help other people to generate new ideas or solutions. Here at Fermilab in Batavia, Illinois, teams of scientists are working together to explore the basic building blocks of all matter. The key here is teamwork and cooperation. Scientists are really just normal people who have a keen interest in their world and the workings of Mother Nature. Through their desire to learn about nature, there have been an unbelievable number of inventions and discoveries made, from electric pop-up toasters to space vehicles that carry people and satellites into orbit. Science is about finding out about things. It's a search for answers. Scientists are always asking questions and then trying to explain things through experiments and observations. A scientist is like a detective gathering clues, investigating leads, and evaluating observations. In the old days, thousands of years ago, the search for knowledge used to be called philosophy. The word philosophy comes from the Greek language. The word philos means loved, and Sophia means wisdom. So philosophy is the love of wisdom. Philosophers were considered to be the wisest of people, and their teachings and ideas were respected without question. One of the most famous philosophers was Aristotle, who lived over 2,000 years ago. He was so respected that people believed anything he said. The problem was, he wasn't a scientist. He never tested any of his ideas. Aristotle once proclaimed that heavy objects fall faster than light ones. Because he had such a reputation as a great thinker, people believed what he said for 2,000 years after he died. In fact, it wasn't until the scientist Galileo Galilei, living in the 1600s, conducted experiments to see if heavy objects fall faster than light ones. He rolled different marbles down a ramp and timed how long they took. He found that weight didn't affect how fast they fell. One story says that Galileo conducted an experiment at the top of the Leaning Tower of Pisa. The story says that he dropped two different-sized cannonballs. This really isn't the Leaning Tower, and this is an actor, not Galileo. The actor will drop a softball and a shot put instead of cannonballs. Well, here it goes. And the two land together, even though the shot put is many times heavier than the softball. Aristotle was wrong, but people believed what he had said for so long because it seemed to make sense. Aristotle probably observed something like an acorn fall and hit the ground, and then he probably compared that to something lighter, such as a leaf. Observing the falling of these two things led him to believe heavy objects fall faster than lighter ones. He never tested his ideas. A scientist doesn't make statements of fact unless he or she has backed it up with experiments and tests. That's what separates philosophers from scientists. What Aristotle forgot to take into consideration was the effect air pressure has on falling objects. For instance, these two pieces of paper weigh exactly the same. One is crumpled up, and then the two are dropped together. The crumpled one lands first because air gets in the way of the uncrumpled paper. In this case, the book is hundreds of times heavier than the single sheet of paper. If we drop them together, the book lands first. However, if we put the paper on top of the book so that air doesn't get in the way, the two land together. In the vacuum of space, where there are no gases to get in the way, all things fall at the same rate. In fact, these Apollo astronauts conducted an experiment to prove that Galileo was correct. A hammer and a feather were dropped together on the surface of the moon. As you can see, they land together. The word science comes from an old Latin word, scientia, which means knowledge. Science is becoming so specialized that it is being divided into smaller and smaller areas or fields of study. There are physicists, botanists, chemists, and biologists, and many more. The suffix ist means one who specializes in something. Galileo and the Englishman Francis Bacon are considered the founders of a method of investigation that is now referred to as the scientific method. This method was introduced in the 1500s. It is organized into logical steps. The first step was to recognize a problem. This meant observing nature and the world around us and recognizing a problem. Next, a hypothesis, which is an educated guess, is established. This is a way of explaining the problem or situation. Then, a prediction, or series of predictions, is made to explain the consequences of the hypothesis. Next, experiments are performed to test the predictions and the hypothesis. Finally, the results of experimentation are evaluated and a conclusion concerning the original hypothesis is established. Scientists are wrong more often than right, but they use this newly gained knowledge to help establish a new hypothesis. Scientists must know how to deal with failure. When data and results of experiments don't turn out as expected, they must rethink the problem and establish new ideas and experiments. If a hypothesis stands up to many experiments, then it can become a theory. If a theory seems to be correct in all cases, it will become a scientific law. However, theories and laws can change. They are being tested all the time. If a new observation shows a theory or law to be incorrect, then it is changed or even dropped. This method has been used throughout the world for the past few hundred years with great success. Yet, as good as the method is, it does not account for all scientific discovery. There have been many cases of discovery by trial and error. An example is that Thomas Edison tested hundreds of metals for the filament of the light bulb before he found the right combination of a tungsten wire in an airless environment. Sometimes scientific discoveries are made by accident. Becquerel found out about radiation when he placed a radioactive sample of uranium in a drawer with unexposed film. Later, when he went to the drawer, he found that something had exposed the film and a connection was made to the uranium sample. Success in science has to do with a common attitude among scientists to strive for answers through experimentation. Scientists have a natural curiosity about nature and how it works. As you can see, observation is a very important part of the scientific method. Observation is needed to discover a problem. Then, during the process of experimentation, observations are critical to collecting data and results. It is important for scientists to be careful observers because it is possible for our senses to be fooled. Read the message to yourself. Did you read, "She saw the birds sitting on the birdhouse"? Well, look again, because it really says, "She saw the birds sitting on the birdhouse." Our sense of sight can be fooled if we aren't careful. Over the years, scientists have tried to develop equipment that can help with observations. One important discovery was made by an amateur scientist named Anton von Leeuwenhoek, who was interested in finding out about pepper. He thought that pepper must have a very gritty, sharp surface because it can make us sneeze. He made magnifying lenses and a simple microscope that were the most powerful of his day. He made an instrument to help the sense of sight. This led to better and better magnifying instruments that can open up the invisible world of the extremely small to our vision. He found that pepper was really round and smooth, which disproved his hypothesis, but it led to so much more. It wasn't long before he started looking at pond water and found one-celled animals swimming about. One experiment can lead to other ideas and further experimentation. Here is an ongoing experimental site in the Great Smoky Mountains. The scientists here are interested in finding out more about the effects of ozone on plant life. They have set up these domes to house different test situations. Each dome has the same number and variety of plants to be studied. All plants receive the same amount of water and sunlight. The water and sunlight are called variables. Anything that may change or vary in appearance or form is called a variable. When conducting an experiment, it is important that the variables are controlled so that only one variable is tested. In the case of this ozone experiment, the variable is the amount of ozone gas introduced into each of the different domes. Each dome receives a different amount of ozone gas. One dome receives no ozone gas. That dome is the control for the experiment. The control in an experiment is the standard for comparison. Results from the other domes will be compared with the control. Every day the plants are measured for growth. The number of leaves are counted, and the height of each plant is recorded. These scientists even have a special sensor that can determine the amount of photosynthesis that takes place. The sensor compares the exchange of carbon dioxide and oxygen from selected leaves and then can determine the amount of food making carried on by the plant. When experimenting, scientists must be sure that they are only testing one variable. They must have more than one test subject, and obviously careful observations and recorded data is crucial to understanding the outcome. So, in review, the scientific method developed by Galileo and Bacon back in the 1500s has helped scientists worldwide organize their approach to learning about our world. The method itself is organized in a series of steps, starting with recognizing a problem. Then additional observations are made to learn as much as possible about the problem. Then a hypothesis or educated guess is made to try to answer the question or problem at hand. Then an experiment is developed to test the hypothesis. During the experiment part of the process, care must be taken to only test one variable. A control is needed for comparison. Data and test results must be carefully observed and recorded. Once the experiment is completed, the results are analyzed and interpreted. If the hypothesis is disproved, then it is rejected, and a new hypothesis may be written. If the hypothesis holds up to the experiment, then further testing may be carried out. If it continues to hold up under many experiments, it may become a theory. And if the theory seems correct in all cases, then it may become a scientific law. Scientists must be able to deal with disappointment and failure. They should understand that each failure adds to knowledge and can lead closer to the final solution to problems. Scientists have inquiring minds that want to discover answers to the challenging questions of our natural world. Technology is the use of science in a practical way. Signs of technological advancement are all around us. Science and technology are not the same, but they are connected. Scientific knowledge is used to develop new inventions, and new inventions help to make further scientific discovery. And it's the desire of scientists to find out about the unknown that keeps the whole sequence going. Back in the early 1900s, the United States Patent Officer in charge of patenting inventions suggested that the office be closed. He reasoned that everything useful to man had now been invented, and therefore the office was no longer needed. He made a slight error, especially when we consider everything that has happened since the early 1900s. There will never be an end to the human desire to create, invent, and explore. Humans are interested in knowledge. Discoveries of one kind lead to fresh questions and problems. It is a cycle that will never stop.
Measurement is happening all around you. How far did the car drive? How much flour for the cake? How fast can you run? And what is the temperature for today are all examples of daily measurements. Humans have used systems of measurement for thousands and thousands of years. Most of the early systems were totally based on body parts. For instance, the Egyptians used units such as the digit, which was the width of a finger, the palm, which was the distance across your 4 fingers, the span, that extended from your pinky to the tip of your thumb, and the cubit, which was from the elbow to the tip of the middle finger. So to measure a table, we might say 1 cubit, 1 span, and a digit wide. The nice thing about this system was everyone carried the necessary measuring tools with them at all times. However, what would happen if everyone in your class was asked to measure a lab table and then construct a cardboard model of the lab top at home? What would we find the next day at school when everyone brought in their cardboard models? Did you think they would all be different sizes? No, actually, they would all be the same as long as everyone measured carefully. You were probably thinking that everyone has different sized digits, palms, spans, and cubits. And you're right. As long as each person is using their own measurements and their measuring tools that they carry with them, then their model should be the same size as the original tabletop. However, if someone forgot their measurements at school and they called a friend for the missing information, there would be a problem. So even though the system was based on body parts, it worked as long as one person did the measuring. The problems arose when someone in one town asked to have a stool made and gave measurements with their units when the craftsman ended up using his units. Unless the people were exactly the same size, there would be trouble. The English used units of measurement that were set and established by kings, queens, and other rulers. In fact, this measuring device is called a ruler because it was probably based on a ruler's foot size. Of course, the problem was that as new people took rule, their body parts became the new unit of measurement. It was finally decided that the units of measurement needed to be standardized. That is to say, they needed to be agreed upon as a certain amount or length. As an example, the English used the length of Queen Elizabeth's arm as the value of a yard. The French were also trying to decide on a system of standardized measurement in the 1700s. They didn't stick with a system based on body parts such as the English. Instead, the French invented a new system based on the meter as the base unit of length. The French had just calculated the distance from the North Pole to the equator and decided to make 1/10,000,000th that distance the length of a meter. They made a master copy of this distance on a bar of metal made of platinum and iridium. This bar is kept in a vault under the same temperature both night and day so that it won't expand or shrink. This new system that the French developed is easy to use because it is based on powers of 10. For measuring lengths greater than a meter, units were used that were 10 times, 100 times, and 1,000 times larger than the meter. The decameter is 10 meters. The hectometer is 100 meters, and the kilometer is 1,000 meters long. For measuring lengths smaller than a meter, the decimeter, centimeter, and millimeter are used. The decimeter is 1/10 the size of a meter. The centimeter is 1/100th the size of a meter. The millimeter is 1/1000th the size of a meter. Another way of thinking of these small units is that there are 10 decimeters in 1 meter. There are 100 centimeters in a meter. There are 1,000 millimeters in a meter. This system is used all over the world. In fact, the metric system is the most popular system in the world. The sad thing is that the United States is the only major country that still depends upon a system based on Queen Elizabeth's arm. Not even England, the country that developed the system, uses it any longer. England, like the rest of the world, uses the metric system. Scientists worldwide use the metric system because it is logical and easy to use. Let's look more closely at the system to see why it's so popular. First of all, as stated before, it is based on powers of 10. There are base units of length, volume, and mass. The unit for length is the meter. The base unit for volume is the liter, and the base unit for mass is the gram. Then all people need to know are prefixes that identify the different larger or smaller units of measurement. There are 6 prefixes to remember for all these possible powers of 10. Here they are. The prefix deca means 10 times greater. Hecto means 100 times, and kilo means 1,000. On the other side of the base units are these prefixes. The deci means 1/10th. The prefix centi means 1/100th, and the prefix milli means 1/1000th. The prefixes always mean the same thing, whether we are talking about meters, liters, or grams. Scientists use graduated cylinders to measure volume. Volume is the amount of space a substance occupies. The graduates come in different sizes, but are all marked off in easy-to-read divisions. Here are 3 different sized graduates. Which would be the most exact? If you look closely, you will see that the smallest graduate is marked off with the most exact markings. When reading a graduated cylinder, care has to be taken. As you can see, the fluid you are measuring is curved inside the cylinder. To determine the level of the fluid, a scientist looked at the bottom of the curved surface. This is called the meniscus. The mark closest to the meniscus is the reading of that liquid. When making a reading, it is essential that the graduated cylinder is sitting on a flat, smooth surface. You can't get a good reading while holding the cylinder in your hand. To measure mass, a platform balance or a balance scale is used. The object being massed is compared with the mass of known measures. In the case of the platform scale, the unknown is placed on one side and known masses are used on the other side to reach a balanced condition. The known masses are totaled to determine the mass of the object. On a balanced beam, known weights are already attached to the scale and are simply moved over to reach a balanced situation. Either of these scales can be used to get very exact results. They can measure as little as 1/100th of a gram. When you consider that a paperclip is about 1 gram, you can see that these instruments are very exact. Here is an equal arm balance used for very small measurements. Notice that this is a very delicate and precise instrument. This brings us to an often confused concept of measurement. The terms weight and mass are often thought of as the same thing. People use the two terms to mean the same thing. This is a grave mistake, because weight and mass actually measure 2 different things. Weight is the amount of gravitational pull on an object. The weight of an object is a determination of how strongly gravity is pulling down on that object. We usually measure weight with a spring scale. A spring inside the scale is stretched by the pull of gravity on the object. But strength of gravity changes from place to place. For instance, a person who weighs 60 kilograms on Earth would only weigh 10 kilograms on the Moon. The Moon is about 1/6 the size of the Earth, and therefore has much less gravity. That's why this lunar rover is bouncing around so much on the Moon, where everything would weigh less. However, the mass of an object isn't affected by changes in gravity. That's because the mass of an object is a measure of the amount of matter in an object. If we take the balance scale to the Moon, the weights are affected as much as the object being massed, so the reading is the same as on Earth. For most situations on Earth, mass and weight will appear the same, but it is important to know that they are really measuring different things. Now let's see how easy it is to make very precise measurements using the metric system. If we were to measure the length of this piece of wood with a meter stick, this is what we would get. The piece of wood isn't as long as the meter, and it comes closest to the 73 mark. The 73 stands for 73 centimeters. So we could say the wood is 73 centimeters long. If for some reason we needed this length in different units, we could easily make the conversion. That's because the metric system is based on powers of 10, and it's a decimal system. Our money system is a decimal system, and I bet you do just fine with it. So here is how we change from one unit to another in the metric system. We'll use this chart to help show what's going on. The board is 73 centimeters long, so we'll write that here under the centimeter column. Now, if we need to know how many meters that is, we will just move the 7 and 3 over to the meter column, and then move the decimal point the same number of places in the opposite direction. See, we move 2 places to the right on the metric chart, so we will move 2 decimal places to the left on the number. Our answer is 0.73 meters. In fact, all of these numbers represent the same amount. They're just written with different units. Notice the digits, the 7 and the 3, stay the same. The thing that changes is where the decimal point is written. This makes the metric system a much easier system to use when converting from one unit to another. If we measured the same board in the English system, we would get 28 and 11/16 inches. To change this measure into feet, we would have to divide 28 by 12 because there are 12 inches in every foot. There's a great chance for making a mistake when you have to divide or multiply numbers. Remember, in the metric system, there is no need to divide or multiply, just move the decimal point. Also, the metric system uses decimals instead of fractions. There would be no reason to learn fractions if we used the metric system instead of the English system. Yes, you heard me right. Just imagine, no need to add, subtract, multiply, or divide with fractions. No need for equivalent, improper, mixed, and proper fractions. The only time we use fractions is when we measure in the English system. Let's look at another example of converting from one unit to another in the metric system. How much juice do we have? Well, we pour it into a graduated cylinder and find that it is between the 40 and the 50 mark on the cylinder. The lines on this graduate mean milliliters, so the volume of this liquid is 45 milliliters. We can easily change this to any other unit by moving a decimal point. Now, if we had a larger amount of liquid, let's say 1.5 liters, we could change it to any unit easily. The number of milliliters is 1,500. Remember, no multiplying or dividing with awkward units. Just move the digits and then move the decimal point, which is like multiplying or dividing by 10. Temperature is another important measurement that scientists use in their work. There are 3 different temperature systems that are used. You are probably most familiar with the Fahrenheit system that is used in the English system. In 1714, Gabriel Fahrenheit invented a system for making measurements of temperature. His system was based on what he thought would be the lowest possible laboratory temperature. In his day, the lowest temperature came from a mixture of ice and salt. He placed a glass tube filled with mercury in such a mixture, and when the mercury stopped dropping, he marked the spot and labeled it 0. It is thought that to get his other reference point, he put the thermometer in an assistant's mouth and marked that spot 100. He then divided the distance between these two spots into 100 equal markings. Each mark was a degree. On this scale, water freezes at 32 degrees and water boils at 212 degrees. In 1742, Andreas Celsius, a Swedish scientist, designed a new thermometer. It was based on 100 steps, so was called the centigrade scale. Centi means 100. Celsius decided that 0 would be the freezing point of water, and the boiling point of water would be 100 degrees. He then divided the distance between the two into 100 equal divisions. In 1828, Lord Kelvin, an English scientist, suggested a temperature scale that was based on a very cold temperature called absolute zero. Absolute zero is the temperature at which matter would stand still and have no heat energy at all. On the Fahrenheit scale, absolute zero is at minus 459 degrees. So Kelvin established this point as 0 on his scale, and then he applied the Celsius scale to that, using the same spacing between degree marks. On the Kelvin scale, the freezing point of water is about 273 degrees, and the boiling point of water is 373 degrees. On the Kelvin scale, there are no negative numbers. Of these three temperature scales, the Celsius scale is the one used by most scientists. When using thermometers, it is important to treat them with care. Never shake a thermometer the way you shake a home thermometer. Don't ever place the thermometer in your mouth. In a lab, you never know where the thermometer has been. Don't use a thermometer to stir things. Use a stirring rod instead. Don't set the thermometer down in such a way that it could easily roll off the lab table. Remember that thermometers are made of glass and they can break easily. Most lab thermometers are filled with either red-colored alcohol or mercury. Scientists are constantly comparing different forms of matter. All of these instruments of measurement help to determine characteristics of specific substances. One important quality of a substance is the density of the material it is made from. Density is the mass of a substance per a certain unit of volume. Maybe you remember the old joke about which is heavier, a ton of lead or a ton of feathers. Well, they each weigh a ton, so neither is heavier than the other. However, the feathers would require much more room because their density is much less than the density of lead. Each kind of matter has its own density. So one way to identify substances is by calculating their density. To do that, we must know the volume and mass of the object. Density is equal to the mass divided by the volume. Mass of something is found with balance scale. The volume may be a little more challenging to find. If the object is shaped like a box with straight sides and edges, then we simply measure the length, width, and height of the object. Then we multiply the three numbers times each other to get an answer. The formula is length times height times width. For an object with an odd shape, we can use a special method called water displacement. An object submerged in water will displace or push aside an amount of water equal to the volume of the object. So we can measure the volume of this rock by first recording a starting amount of water in the graduate. Then when the rock is lowered into the graduate, the water will rise. The new level is recorded, and the difference between the two water levels is compared. Subtract the starting level from the final level to get the volume of the submerged object. It just so happens that 1 milliliter of water equals 1 cubic centimeter. So every milliliter of water that rises is equal to 1 cubic centimeter of volume. The density of water happens to be 1 gram per cubic centimeter. The density of this piece of wood can be determined by measuring the mass and volume of the wood. Mass is 10 grams. Volume is equal to length times width times height. Each side of the cube of wood is 2.5 centimeters. So here is the calculation. As you can see, the volume is 15.625 cubic centimeters. Density is equal to mass divided by volume. The mass is 10 grams, and the volume is 15.625 cubic centimeters. So the density of the wood is 0.64 grams per cubic centimeter. If we place the wood in water, it floats because the density is less than the density of water, which is 1 gram per cubic centimeter. So objects with densities greater than water sink, and objects with densities less than water float. Well, today we have explored the way scientists gather information through measurement. Tools have been developed to help them do their job. To get accurate readings, people have to be careful in their approach to measurement. For instance, when using a ruler, make sure you're lined up correctly. If you look closely at the ruler, you may see it is damaged at the end. One solution is to make your measurement from the first centimeter mark. Just remember that you have moved in 1 centimeter, so subtract 1 from the measurement you get. Measurement is important to us all. To scientists, it is critical to analyzing and evaluating their experiments.